Hi guys. Okay, so let's look at chapter 6, ionic and molecular compounds. First, let's look at what is the ionic and covalent bonding. Next, how are the ions formed, that is the cations and the anions. Then the charges and the group numbers, orbital diagrams of the ions, then writing the formulas. Now these formulas in your book are scattered all over the chapter. However, I have condensed all that information in the worksheet. So in the worksheet, you're going to look at the metals and the non-metals and how the ions are, how the bonds are formed in them. Then the metals that have more than one type of positive charge, then the polyatomic ions, and then the hydrates, the covalent bonding naming, and the acids. And you can leave out, I'm going to just put it here in the worksheet, the organic compounds. Organic naming is optional. If there is time, we will cover it. Otherwise, we will leave it. Anyway, so let's look at, first of all, ionic bonds and the covalent bonds and how are they formed. Ionic bonds are formed by the transfer of electrons. And covalent bonds are formed by sharing of electrons. Okay, now when the transfer of electrons occurs, there's the metals and the non-metals. They are involved in making the ionic bonds. So metals give electrons, okay, and what do they form? They form cations. And what are cations? Cations are those species that have a positive charge. Okay, so plus charge. Next is the non-metals. The non-metals are non-metals, they accept electrons. So they take electrons that are given by the metals. And then they are called anions. And these have negative charges, okay? They form a negative charge. And how many negative charges, how many positive charges, all that is governed by the octet rule, by these rules. So first of all, octet rule. Octet rule is every metal and every non-metal want to have 8 electrons in the last shell. So that's one piece. Just make this small. 8 electrons in the last shell. So they want to have 8 electrons in their outermost shell. Okay, that outermost shell then begins to look like, or the energy level that begins to look like the nearest noble gas. Okay, now they want to have the nearest noble gas configuration. Now, not all of them follow the octet rule. There are some exceptions. So that is why the nearest noble gas configuration, like helium, doesn't follow the octet rule. So they would like to look like helium. Okay. And the third rule is, besides that, there is also the whole reason why they are going to do this is because they want to achieve stability. Stability is stable. They want to become stable. So that octet rule makes them stable, means less energy, less motion. Okay, so this is the reason why they are, they give away the electrons or they accept the electrons. So because then they begin to look like the nearest noble gas, would have 8 electrons in the last shell. But at the same time, what about those elements that are the inner transition and post-transition. Now, these are the D and the F block elements. Okay, the D block elements. So for your course, just keep it to D block elements. So what is the deal with them? For them, how are they going to become stable? These guys become stable when they have a half-filled or full-filled subshells, okay, or orbitals. So here's the rule for them, that half-filled half filled, and or full filled. Full filled orbitals are more stable. Orbitals are more stable. So that is why they give away the electrons based on that. So these are generally the inner transition and post, this should be N here, post-transition metals. These are all D block elements. These are all metals. So these metals have, these metals, all the metals, they give away electrons. Okay, so that's one thing. Now there are non-metals, okay, non-metals. These guys, they connect with themselves or they bond to themselves. So how do they bond? They bond by sharing. Sharing of electrons. Sharing of electrons, and these generally are the non-metals. So in this case, again, they share because they're so close to the nearest noble gas. Generally, most of the non-metals are very close to noble gases. So this is the reason why these non-metals, they sometimes, if they react to themselves, they react among themselves, okay, among themselves. So to form bonds, okay, and these bonds are the covalent bonds, okay. So this is the very basic broad overview of the two types of bonding, the covalent bonding and the ionic bonding, and both of them, they relate to this. The whole idea of bonding is to attain stability, and that stability can be achieved by, you know, either sharing or by giving away or taking in electrons. Now let's look at the scenario where the let's look at, first of all, the group numbers and the cations and the anions, how are they forming in the group numbers. So this part was, first is this introduction. Next is the group number and the charges. Group numbers and charges. So how do we get that? Here you will have the group number, let's write this down, and charges, and the number of bonds they form also. Bonds and valence electrons. VE stands for valence electron. So, okay. So here is the group number. This is how many valence electrons they have, the last electrons. Then the charge, you know, and that charge relates to the number of bonds, how many bonds they form. So let's look at this one. So elements that are in group 1A. Now these are the representative elements. So group 1A have one valence electron. Okay, one, and I'll put this as VE, one valence electron. Charge is +1. So they give away the electrons, and this is one bond they can form. Group 2A, all the elements that are in group 2A will have two valence electrons, and they form +2 charges, and they form 2 bonds. Now, group 1A is all, you know, lithium, beryllium, lithium, sodium, potassium, rubidium, cesium, francium. Okay. So let's put this here in small. So this is, these guys are lithium, sodium, potassium, rubidium, cesium, and francium. Okay, so they will have all +1 charge. Group 2A is beryllium, magnesium, beryllium +2, magnesium +2, beryllium, magnesium, calcium +2, barium +2, and strontium +2, sorry. Magnesium +2, calcium +2, barium +2, and strontium +2. Okay, so this is the deal with the group 2. Then comes group 3A. Group 3A has 3 valence electrons plus 3 charges, can form 3 bonds. And here, since we're talking about the metals, so here we have aluminum as a representative element plus 3 charges. And then the rest of them will form variable charges. Variable charges, the rest are variable. Okay, and we will talk about the variable one. Next, we have the group 4A. Now 4A has 4 valence electrons, and it can form 4 plus 4 charge, can form minus 4 charge, and can form by the sharing of electrons. So regardless, there are going to be 4 bonds. And in this case, basically, because group 4A also has the metals, non-metals, metalloids. So that is why we are going to just put it as variable. Because there are other variable also. Because there are metals, remember that. So this contains metals, non-metals, metals and metalloids, yeah. Metals, non-metals, and the non-metal here is carbon. And then we have metalloids also. So that's why it's variable in the group 4A. Next comes 5A. 5A has 5 valence electrons. Okay, but it will form minus 3 charge and 3 bonds. And which ones are the ones? It generally, for the 5A, we have a nitrogen and phosphorus. So with the charges, and then the rest is variable. Nitrogen minus 3 charge, phosphorus minus 3 charge, and the rest is variable charges, because on this side again there are metalloids and the metals also. Post-transition elements, remember. Okay, next is we have 6A. 6A has 6 valence electrons, and it will form minus 2 charges. There are 2, it will form 2 bonds, and the elements that are the non-metals that are here is oxygen with minus 2 charge, sulfur minus 2 charge, selenium minus 2 charge, and the rest is again variable. Variable applies to the metalloids and to the metals, the post-transition ones. Next comes the 7A. 7A is 7 valence electrons, and the charge is minus 1, and the bond is 1. And which ones are here? The ones that are here are fluorine minus 1, chlorine minus 1, bromine minus 1, iodine minus 1. Okay, so these guys. Next comes the group 8A. Now 8A does not form. There are 8 valence electrons, right? And so there are going to be no charges and no bond. But there are exceptions, and there are exceptions to the rule, which we will discuss in a minute regarding. So this is generally applies to here. Let's do this here. This part here is the metals. These are metals. And these guys are non-metals. And just keep this in mind that on the P block, the non-metal side, there are also the metalloids and the metals, which are going to give you more than one type of positive charges. So let's look at those first of all. So this was our general trend that relates to the representative elements. Representative elements. Okay, representative elements. Next is we are going to look at the elements, rather, which are metals. Okay, metals that form more than one type of positive charge. Now, these are, as we said, these elements are the transition elements and post-transition elements. Okay, post-transition. Now, post-transition means that they are, they could be, as we said, they are metals and also metalloids, or rather, wait a minute. Maybe, okay, metalloids, I can't say, okay. Transition metal, or rather you can say D block metals for your course. Just keep it that way. Okay, so these guys. So which ones are those? Now, here's the thing. Just give me 1 minute. I'll show you in the in your handout. There's a table. So I'll show you in a minute. Hold on. Okay, so what you see on the board on the left on the screen is the table that is present in the handout. So in this handout, you will see table 6.5, and this is, I think, on page 5. And the pages are not very clear on the handout, so feel free to put your own pages. And also, this is a very limited information. So, you know, obviously, you can't learn all of the things that are in the tables, but you should know how to refer to them or where to refer them. So that is where it is. And some of the pieces that are not there or missing, or you see in other books and you don't see them here, you're welcome to put your own notes, and that's fine. Okay. So here we have table 6.5. And in that table, we will see the elements such as, look at this, bismuth. Bismuth can form more than one type of positive charges, +3 and +5. Similarly, chromium. Similarly, cobalt, copper, gold, iron, lead, manganese, mercury, nickel, tin, you know, and there are more. So I'm going to now bring it here. So let's look at these, the elements that form more than one type of positive charges. For example, bismuth. Now it's very important you know the names and the symbols. So bismuth can form +3 charge, and bismuth can form +5 charge. Okay, so how will you write this? You're going to use the Roman numerals. Bismuth 3, like that. Okay, and bismuth 5. Bismuth 5. Okay, now, I think I should just hold on to this. We should bring these here. Okay, let's do this Roman numerals first, just to refresh your memories. Roman numerals are Roman. They are used in, you know, naming these type of elements, numerals. So for Roman numerals, we write 1. This is equal to 1. This stands for 2. This stands for 3. This stands for 4, right? And this stands for 5. This symbol stands for 6. This symbol stands for 7. This symbol stands for 8, right? And this symbol stands for 9. This symbol stands for 10. This one is 11. And this one is 12. Okay, and so forth. But we are not going to go that far. So generally, you know, for us, we look at the generally 1, 2, 3, 4, 5, you know, generally up to this level. Okay, so now let's look at this. So we have bismuth, we show as this. Also keep this in mind that lower oxidation state, these are also called oxidation states. Oxidation state, you know, or these more than one positive charges. Let's put this here. More than one type of positive charge. So that is called that positive charge is also called the oxidation state. OXIDATION. Okay, oxidation state. And then more than one type of positive charge oxidation state. This also means variable valence state. This is also called variable. So all these terms are used. Variable valence state. Okay. So another thing here is very important, and that is lower oxidation state. Lower oxidation state. Lower, lower charges, you can say, lower number of charges, end in us, OUS, and higher charges, the number of charges are going to end in ic, IC-ic. So this becomes bismuthus, bismuthus, THOUS, and this becomes bismuthic, THIC. Okay, so this us relates to a lower state, and this ic relates to a higher state. Okay, now let's look at another example. And again, this is specific to the element. For example, copper. Copper has +1 state, and copper exists in +2 state. +1 and +2. +1 state we express as copper 1. Okay, and this is also called cuprous, and this one is copper 2, and this is called cupric. So this is cuprous or OUS, and this is cupric. Okay, cupric. Next is, let's look at another state of iron. Iron exists in +2 state, and iron exists in +3 state. In +2 state, we write down iron, okay, iron and 2. And then this is iron 3, 1, 2, 3. Okay, so this becomes ferrous or OUS, and this becomes ferric or RIC, ferric. Okay, so again, higher oxidation state and lower oxidation state. Higher, lower, sorry, different color. Okay, so the lower is, this is the lower, and the higher is, I'm going to put this in green color, ic, plus and +2. All right, besides that, let's look at another ones. Tin. So SN in +2 state and SN in +4 state. So this becomes tin 2, and this becomes tin 4. Tin 2 is stannous, OUS, and tin 4 is stannic, NNIC. Okay, so once again, the higher 4 is +4. The lower is us is 2 state +2 state. Again, there's another one, lead, PB +2 and PB +4. So remember that I brought this on purpose. Iron, tin, lead. See, their symbols are different from their names. So this is lead. Again, lead, +2 state, +4 state. +2 state is plumbous, BOUS. And the lower oxidation state is plumbic, IC, plumbic. Okay, so we have us +2 here, and ic is 4 and +4. Okay, and so forth. And there is a huge list which you can add on your own. So we covered the Roman numerals in naming these elements that have more than one positive charges. Now, another thing about whenever you are naming, and so let's put this here. So this was 2A, this is 2, 3, and 4. Okay, next is when you are naming the metals and the metals, the names of the metals generally remain as it is, but the names of the non-metals, now we look at the non-metals. Non-metals end in, if they are just by themselves, non-metals if just by themselves, then their end in, their names end in IDE. Okay, IDE, just the metals. But if the non-metals so are in the, with the polyatomic ions, then their names are different. So let's look at those also, and then we will start the naming. Non-metals which are just by them when they are mixed with the oxygen, if bonded, not mixed, if bonded with oxygens or other non-metal with higher electronegativity, then these are called polyatomic ions. Okay, so non-metals that form polyatomic ions, they combine with either oxygen or another element, non-metal, with a higher electronegativity. So these are the non-metals. Then they will form a charge, right? Non-metals if bonded with oxygen or other non-metal with higher electronegativity, so this will be polyatomic ions. Okay, and then if the non-metals, if just by themselves, by this means that if non-metals just by themselves means if non-metals just by themselves bonded with metals, okay, bonded with metals, then their names end in i's. So now let's look at the concept of polyatomic ions. Okay, before we start with the polyatomic ions, let's look at the capability to form the bonds, the bonding capability in non-metals. Bonding capability in non-metals. Okay, now how is this happening? Bonding capability in non-metals. So normally, yes, we are following these rules right here, the ones that relate to the group numbers. Normally, so this is in ordinary conditions when they are connecting with the metals in that case. So in other words, when the metals are so when these metals, so like these guys, when they are combined with the metals, in that case they will form these charges. Okay, so I'll put this note here that when non-metals when bond with metals, then in that case, yes, nitrogen will have a negative charge, phosphorus will have a negative charge. Here, when the metals bond with non-metals, so we are not looking at the polyatomic ions yet in this case. Okay, so this is what, in that case, they will form these plus charges. So these are with when these forms the when bonded to metals. So in other words, when they are forming the ionic bonds. Okay, so generally these are all ionic bonds. So these charges come only for ionic bonds. okay, when ionic bonds are formed by the transfer of electrons. Okay, next is, let's look at this situation where the bonding capability in nonmetals. So let's look at, first of all the nonmetals that we know of, and those nonmetals are, hydrogen is a nonmetal, right? So let's look at this. Hydrogen, so group 1A, group, so I'm going to just put it like GRP. Group 1A, we have hydrogen. Hydrogen has one valence electron, so it will only form +1 charge, and that is going to be only one bond. Okay. Then comes group 3A, and here we have boron. Boron has 3 valence electrons, and it will generally form bonds by sharing 3 valence electrons, so it will form 3 bonds. Okay, and these bonds are formed by sharing. Okay, next is, let's look at the group 4A. So group 4A, we have carbon and we have silicon. These are the nonmetals. So carbon and silicon each have 4 valence electrons, and these 4 valence electrons are so carbon and silicon will form 4 bonds. Silicon also will form 4 bonds, and like I said, carbons can also form bonds by sharing, and ionic bonds are also formed. So generally sharing is more common, so by sharing. Okay, silicon, so like silicon dioxide, all that is, so it's also formed by sharing. All right, next is, we are going to look at group 6A. Group 5A. Group 5A. Now, which ones are in group 5A? Nitrogen, and we have phosphorus. Now here, nitrogen, when nitrogen has 5 valence electrons, phosphorus also has 5 valence electrons. Nitrogen will form -3 charge. Phosphorus can also form -3 charge. But nitrogen can also form bonds by sharing also. It can also form -3 charge, means it can form 3 bonds. And these 3 bonds can also be ionic bonds, depending if it's combining with the metals, or it can form the covalent bonds if it is forming the bonds with its, with a non-metal. So covalent is always non-metal. Next is phosphorus. Phosphorus will form, here's an interesting 3 bonds, and phosphorus can also form 5 bonds. So when does phosphorus form 3 bonds? And when does it form 5 bonds? Phosphorus will form 3 bonds when it is connected to a lower elements with a lower electronegativity, or some element with bond when, how do I write this? With bond with lower En element with a lower electronegativity. Okay, and we will see in what conditions you do get that. 5 bonds are with an element with higher electronegativity. So let's just put it in a better way. I'm just not feeling good. Okay, so it forms 3 bonds with an element, any element with lower with elements having lower electronegativity. Okay, and it will also form 5 bonds. When does that happen? It forms 5 bonds with elements. So I don't have to write this again and again. I'm just going to put this as this thing here. So let's just do this here with 3 bonds. So just because there are others also, right? Sorry. So 5 bonds here, phosphorus, and 3 bonds, and I will put a star so you know which way. So 5 is an exception. Okay, next is, let's get group 6A. Group 6A. Group 6A consists of oxygen and it consists of sulfur. Oxygen and sulfur, both of them have 6 valence electrons, and that makes them -2 charges, gives them -2 charges. And yes, oxygen will form 2 bonds, right? But sulfur can form 2 bonds, but sulfur also can form 4 and 6 bonds. And 4 and 6 bonds are in the case of, this is an exception. This is an exception, an exceptional case. And in what conditions is that? When they bond with the elements that have a higher electronegativity. Now let's look at this. Group 7A. Okay, group 7A is fluorine, chlorine, bromine, iodine. All of them will have 7 valence electrons. So they will have -1 charge and they will make only 1 bond. But the exceptions are chlorine, bromine, and iodine. They can also make 3, 5, and 7 bonds. So 3, 5, and 7 bonds are also possible. And when does that happen? When they combine with other elements that have a higher electronegativity. So why I'm telling you all this is because this is where the polyatomic ions are formed. Okay, now let's look at this one. Group 8A, fine. We know in group 8A, there is helium, there is neon, Group 8A is helium, neon, argon, krypton, xenon, and radon. And all of them make 0 bonds, no bonds. However, xenon is known to make 2, 4, and 6 bonds. So, you know, in chemistry, that's the thing. You can change the reaction conditions and you can get the, you can change the reaction conditions and you can get, you know, the whatever results you want. So we see that, let's put this here clearly. 4 and 6 bonds. Okay, next is your next is group 8A, and then comes the, where is all this information? In the handout. So if you look at it in the handout, this is present on this page. This page is page 4. So here is the covalent bonds in nonmetals. So here you have the number of valence electrons and all this information that I said is presented in this table right here. Okay, now, and the table that we talked about is also here. So you're welcome to, you know, whatever works for you. But let's look at this now. So let's explain this thing further. So here, these guys, these are the exceptions, and the exceptions are exceptions that when these nonmetals, when the ones that are starred, so the starred nonmetals bond with other nonmetal, and it has to be nonmetal, and another nonmetal that has a higher electronegativity. Nonmetal that has a higher electronegativity. Okay, for example, when they bond with oxygen. Okay, so for example, when they bond with oxygen, such as carbon with not the carbon, let's do like sulfur. When it bonds with sulfur, sulfur makes 2 bonds. So sulfur dioxide, sulfur trioxide, sulfate, sulfite -2 charge, sulfate -2 charge. For example, phosphorus. Phosphorus like phosphorus like phosphite -3 charges. Sorry about that. Okay. And then comes phosphate, PO4 negative charges, right? That's phosphate. So this explains why, you know, these guys will make more than one type of bond is when they're bonded with. So if you look at it here, sulfur is bonded to oxygen. Oxygen is more electronegative than sulfur. Phosphorus is bonded to oxygen, more electronegative. Similarly, you also have like ClO3, 1 negative, ClO4, hyperchlorate, 1 negative. Okay. Similarly, you have bromate, BRO, I think it's BRO3, 1 negative, if I'm not sure. So anyways, bromine is connected to these guys. So again, oxygen, bromine connected to oxygen, chlorine connected to oxygen. So it's making more than one type of bonds. So you will study this more, how this happens. So it was important for me to introduce this. Now, how do you know that which element has a higher electronegativity and which one has a lower electronegativity? So one is the general trends in the periodic table. Electronegativity. One is the electronegativity, and that is one is the trend in the periodic table. Trend in the periodic table. And in that trend, we see electronegativity also relates to the electron affinity. Okay, electron affinity means love for electrons. So electron affinity, AFFINITY. So electron affinity and electronegativity, both of them the same. So what are the trends? So here is this. The trend is in a periodic, you go from top down, top to bottom, top in the same column to bottom. Or when you move from left to right, what do you see? You see that when you move from left to right, the electronegativity increases. So electronegativity increases. Electron affinity, electronegativity is En, and electron affinity is Ea. Okay, and electron affinity increases. Okay, when you go from top down, electronegativity decreases and the electron affinity also decreases. So both of them go side by side. Okay, so when you move from left to right, when you compare the elements in the same period, then the ones that are more towards the left hand side will have a higher electronegativity. The same is the case here in the same column. If you move from top down, you will see this. Okay, this is one piece. Next is you're going to look at the handout, and these values are given. Handout, look at let's go back here. Okay, so here we see these values are right here. So this is on page number, I think it's page number 8, page number 8. Okay, so this table you see on page number 8 lists the values of the electronegativities. So you see it's from 0 to 4, the 4 being the highest and 0 being the lowest. So the highest is of fluorine, and if you look from the top down, it's decreasing. Fluorine is 4.0, chlorine is 3.0, bromine is 2.8, and iodine is 2.5. That's the electronegativity, decreasing from bottom to top, as from top to bottom as you go down the column in the periodic table. Now let's look from left to right. Carbon is 2.5, nitrogen is 3.0, it's increasing. Oxygen is 3.5, it's increasing, and fluorine is 4.0, it's increasing. So as you move from left to right, it's increasing. So in other words, now between chlorine and oxygen, so you can just look at these numbers. When chlorine combines with oxygen, then its capability to make more bonds, it increases, it comes out. So it has that potential to make more bonds. When chlorine combines with hydrogen, hydrogen has low electronegativity. Hydrogen has 2.1, chlorine has 3.0, right? So 2.1 and 3.0, that we will see that Chlorine is 3.0 and hydrogen is 2.1. So hydrogen has less electronegativity. Chlorine is only making one bond. But when chlorine combines with oxygen, which is a higher electronegativity, then chlorine can make 3, 5, and 7 bonds. Okay, so that's what it is. So that's where the concept of the, so this was on page 8 are the electronegativity values. And these electronegativity values are on from scale 0 to 4, 4.0. 4.0 is the highest, or anything that's close to 0 is the lowest. Okay, so we see that when, so let's just write down here, that when chlorine bonds with hydrogen, then chlorine only makes one bond because hydrogen has less electronegativity than chlorine. And you can refer to the table. Electronegativity of chlorine is, electronegativity of the chlorine from that table is 3. One second. 3. Chlorine is 3.0 and hydrogen is 2.1. So this is happening. But when chlorine bonds with oxygen, then chlorine can make 3, 5, and 7 bonds. Okay, depends how many oxygens it's combining. Okay, so we will look at that. So here we see that chlorine, the electronegativity of chlorine is 3.0, but the electronegativity of oxygen is 3.5. So the oxygen's electronegativity is higher than the chlorine electronegativity. So therefore, chlorine is going to expand its capabilities to make more bonds. So this is, so you know, some of this information is not in your book, not in the chapters, nowhere in the book, but I'm explaining this because comes the question that why are there these polyatomic ions making all these different bonds? From where is that coming when we talk about where your book is only giving you this information? So that this is where, you know, the reason comes. So let's now look at the polyatomic ions, and then after that we will start naming. Okay. 5, 4, no, so this is the, so this one was 5, this is 6, 6. Okay, now 6. Now we are going to look at polyatomic ions. Okay, now pay attention to this. When carbon, now here is the concept of maximum. So here, let's do this here. This is the oxidation state. Oxidation state. Oxidation state means, you know, when it's bonded with oxygen. Okay, bonded with oxygen. Okay, here the oxidation state was the plus the positive charges. Oxidation state is the variable valence state with plus charges, That is also called in the case of metals. Okay, that's the case of, this is the situation with the metals. Now we are looking at the non-metals. Okay, when we are talking about the non-metals. So in the non-metals, when they combine with each other, they form these polyatomic ions. So lower number of oxygens is going to be ending in us. And wait a minute, sorry, phosphate, ite. It is ite, I-T-E, and higher number of oxygen is 8, ATE. Okay, now let's look at these polyatomic ions. So when you have, let's do it with this color. Okay, when you have carbon, combining with oxygen. Now here also, the maximum number of oxygens that can be connected with, only one maximum number of oxygen that can be bonded. That is ending in ATE, ATE. The whole thing about 8, okay? So maybe this is a little bit misleading. ATE, okay? All right, so carbon, the maximum number of oxygens that carbon can combine is 3. And when it does that, it acquires 2 negative charge. And the name is carbonate, ATE. Okay, let's look at nitrogen. Nitrogen, maximum number of oxygens that nitrogen can connect, the lower number, nitrogen can connect with 2 oxygens, and the maximum number it can connect is 3. It can combine with 2 nitrogens and it can get -1 charge. It can combine with 3 oxygens and it can get -1 charge. Lower oxidation state is nitrite, ITE, nitrite. You know, so some of these things you just have to memorize. And this is nitrate, ATE, ATE. Okay. Next comes the one second. So we got the nitrogens, we got the, let's look at sulfur. Sulfur can combine with 3 oxygens and have a 2 negative charge, and sulfur can combine with 4 oxygens and have 2 negative charges. So the lower oxidation state is sulfite, ITE, and a higher oxidation state is sulfate, ATE. Okay, similarly, phosphorus. Phosphorus has a capability to combine with 3 oxygens and have 3 negative charges. And phosphorus can also combine with 4 oxygens and have 3 negative charges. Lower oxidation state is phosphite, ITE. Higher oxidation state is phosphate, ATE. Okay, so next is, similarly, we have, for example, here, interesting, chlorine. Chlorine can combine. In the past, we knew that only chlorine could combine with 3 oxygens. That was just discovered. So they said, okay, fine, 3 oxygens, and we also find chlorine combining with 2 oxygens with 1 negative charge. So we said, okay, higher oxidation state, chlorate. Okay, and lower oxidation state, chloride, ITE. But later on, they also discovered that, hey, chlorine can combine in very special conditions. See, in chemistry, you can change the reaction conditions and you can get, you know, different types of products. So they were said, hey, chlorine can combine with 4 oxygens, which is higher than chlorine, and chlorine can also combine with just 1 oxygen and still be stable. So like polyatomic ions are stable in a way. So then we said, okay, then what is the name then? So how do we name this? So this, the name was, we didn't change the chlorate, but we said, okay, it's higher than chlorate. So perchlorate, higher than chlorate. So that's perchlorate. And this is hypo, HIPO, lower than chloride. Okay, so that's the name, chloride. And hypochlorite and chlorate and perchlorate. So this is how they got these names. So all these 4 for chlorine. Okay. All right. Besides that, there are others called a bicarbonate. So when hydrogen combines with oxygen, then this becomes hydroxide. Now this is something that was very past, a long time back, this was discovered. So what they said that, okay, hydroxide. So it's not like the oxygen is coming in the end and hydrogen is coming in the first, but the formula, you see, it's contradictory, but then it got that name, so it stuck with it. So that's what it is. Besides that, if hydrogen combines with the carbonate, -1 charge, then it becomes bicarbonate. And when hydrogen combines with, for example, This is also called a hydrogen carbonate, but bicarbonate is more common. So similarly, when it combines with BHSO4 minus 1, then it becomes bisulfate, by HPO3 minus 2. This is biphosphite. Remember that, phosphite. It's connected to the phosphite ion. So it's biphosphite. Okay, so that's the deal with the hydrogen. Besides that, there are others also, the interesting ones, which are like, for example, if chromium can combine with 4 oxygens, have a 2 negative charge, and 2 chromium, Cr2O7 minus 2, then this is, the name is chromate, and that's what it is. And the chromium connected to maximum number is 4, or this is also dichromate. Okay, dichromate. So, you know, at this point, I mean, we can go on and on. There are many, but you also have a list of these polyatomic ions in the, I think I had it. I don't recall now. I may have put it. Polyatomic ions right here. Okay, so this is on page, and you can add more to it. Okay, you can add more. There are many. Okay, so anyways, this is on page 6. So page 6, table 6.7. Page 6. So polyatomic ions, this is on handout, page 6, table 6.7. And here you should add more from your side. Okay, and there are many in the worksheet also, so just you can, you know, add more to this list. But anyway, this is just to give you the idea of the naming. So as we said, lower oxidation state is all ite. The less number of oxygens are ite. Okay, ite, lower, but higher number of oxygens are ending in ate, like chromate, sulfate. Okay, so that was the chlorate here, chlorate, phosphate, sulfate, and nitrate, and so forth. Okay, all right, so this we get that. And then one last piece is naming the 6 and then 7. And then here we have, when you name the non-metals, when the non-metals combine just by themselves, but they are not without the charges. So non-metals without charges. So these are the non-metals. Polyatomic ions are basically non-metals. Excuse me. Sorry about that. Okay, so polyatomic ions are when the non-metals combines and non-metals bonded with charges. Okay, as you can see. And when the non-metals bond, but without the charges, in that case, what is the nomenclature? In that case, okay, so here we use when only the first non-metal, the name remains as it is. So the first non-metal, generally, first non-metals, the name is as is generally, but there are always, you know, exceptions. As is, if it is like mono. And the second is the second non-metal will have this, you know, these, what are these called? The prefixes, non-metals, prefixes. And what are those names of those prefixes? Those names are, if it's only one, then it's mono, 2, di, 3, tri, 4, tetra, 5, penta, okay, 6, hexa, 7 hepta, 8 octa, 9 nona, and 10 is deca. So, generally, again, for your course, mono, di, tri, tetra, penta, hexa, maybe hepta can be used, but we haven't, we're not looking very complex molecules for this course. So now let's look at the bonding and the naming. Bonding, first of all, 7, this is 8, and that is, let's look at how the ionic bonds formed. Ionic bonds. Okay, so here you have a metal, which is sodium, and here you have another non-metal, which is chlorine. So here, let's look at it. Sodium is 11 electrons we need to place, and 11 electrons, 11, and chlorine has 17. Okay, so 1s2, 2s2, and 2p6, and 3s1. Okay, chlorine is 1s2, 2s2, 2p6, and 3s2, and 3p5. All right, so this means sodium has 1 valence electron. 1 valence electron. That's the Lewis structure. And chlorine has 7 valence electrons. 1, 2, 3, 4, 5. And this is 7 valence electrons. And which ones are those? This is the valence shell. This is the valence shell. Okay. So in the valence shell is the highest shell number, and that is 3 in both the cases. But we see that, the Lewis structures, in the Lewis structures, we only put or Lewis dot structures, we only put the dots, and these are the valence electrons. Okay, now let's look at how they look like their orbital diagrams. In the orbital diagrams, we only show the valence electrons and we leave the rest. Okay, so let's look at this now. So we have sodium, and the condensed form of sodium would be the inner core. The inner core is 10 electrons, right? And this guy also has 10 electrons. So these inner core, we can just put in as neon, the 10 electrons. And the last one is 3s1. Okay, and how do you show it? We show it like 3s1. 3s1 is 1 electron, like that. Single, spin. Now comes the chlorine. Chlorine is neon 10. Okay, and then this is 3s2 and 3p5. So how do these look? 3s2 and 3p5. Let's put it here. Sorry, 3s1 looks like this. And here is this guy, 1 electron, 1 valence electron. Now, in this case, 3s2, p has got 3 orbitals. Remember, s can hold a maximum of 2 electrons. P can hold a maximum of 6 electrons. Okay, but so 3s2 is this, 3p5 is, first you put them singly occupied, and then you pair them, 1, 2. So these are all the 5 electrons. So 5 electrons here, 2 electrons here, 2 electrons here. Okay, so always first singly occupy, and then second you pair. So this is how you create the orbital diagrams. Okay, in the orbital diagram. So you only look at the valence electrons. So what do we see here? We see that these guys are unpaired. This is one unpaired electron. This is one unpaired electron. So in this case, if sodium loses that one electron, or the sodium gives that one electron to chlorine, chlorine has a higher electronegativity. It is going to attract that one electron. So that -1 electron from sodium to +1 electron here. In this case, that one electron is given from sodium to chlorine. So when that happens, what happens next is the scenario where sodium and chlorine, sodium has the inner core of neon 10. Chlorine also has the inner core of neon 10. And then we have 3s0. And when that happens, sodium acquires a positive charge. Okay, it becomes a cation. But chlorine, when it acquires a negative one electron, it gets a negative charge. Okay, so then we have 3s2, and it acquired that one more electron, so it becomes 3p6. So if you look at it, sodium plus, that one electron has gone to chlorine. So that's why chlorine gets a negative charge, and it gets a fulfilled orbital. So this is fulfilled, sorry. This is fulfilled, this is fulfilled, and this is also fulfilled. Okay, so in this case, what is this going to look like? This is obviously now has the inner core of, there is too much disturbance during the daytime. You know, that is why I always do all my recordings at the night time. Like, it's just so much disturbance. Anyway, so please just bear with me and forgive all this you know, distractions. But anyway, so here we have sodium with its inner core shining like that of neon. So it will have an electronic configuration that looks like 1s2, 2s2, and 2p6. So these are 10 electrons, and these 10 electrons represent neon, which is the nearest noble gas. Okay, besides that, look at the octet. 6 plus 2, 8. 6 plus 2 is 8 electrons. Okay, so that is, again, the octet is met. So sodium, when it loses electrons, it meets that octet of 8 electrons also. Chlorine, when it gains the electron, so yes, then it begins to look actually like argon. So argon has 18 electrons. And what does it look like now? So chlorine now becomes 1s2, 2s2, 2p6, 3s2, and 3p6. It has the 8 electrons, 3s2 and 3p6. 6 plus 2 is 8, right? And it begins to look like the nearest noble gas, which is argon. And sodium begins to look like neon. Okay, so that's the reason why sodium and chlorine, they lose electrons. Let's look at another example of magnesium, and we're going to look at the diagrams also. So here you have magnesium, and magnesium with bromine, Mg, or let's do magnesium with oxygen, So we have magnesium, magnesium is 12, and oxygen is 8. Just want to confirm sometimes. Oxygen is 8. Yes, sorry. Okay. So magnesium 12, 1s2, 2s2, 2p6, 3s2, and yeah, 6, 7, 8, yeah, 3s2. That's one thing. And this magnesium can also be written as neon 10, the inner core, which is the inner core. This guy is the inner core. 10 electrons are neon. And then the last one is 3s2. Let's do the orbital diagram of magnesium. Magnesium is neon 10, and then 3s2 is like this, these two guys. And fine, this is paired, and that's okay, you know. So 2 valence electrons but it's paired. So that is why it is in group 2A, 2 valence electrons. Okay. So, but magnesium will prefer to lose 2 electrons. And when that happens, magnesium gets 2+ charges. And then it begins to look like neon, the 10 electrons. It has lost those. Magnesium 12, remember, magnesium is 12, minus 2 electrons. Now magnesium has 10. And so internally, it's looking like neon. So its electronic configuration is 1s2, 2s2, and 2p6. Now look at this, 8 electrons. It has those 8 electrons in the last shell. This is the last shell. This is the last shell, 8 electrons. Okay. Next is the, sorry about that, oxygen 8. Okay. Oxygen 8 will add 2 electrons that the magnesium is going to give. And then it will acquire 2 negative charges. And it will have 10 electrons with that. And yes, it is going to look like neon. So here we have oxygen, which was 1s2, 2s2, and 2p4. Okay, so this is oxygen. Oxygen is if you look at the orbital diagrams of this one, the last one, that is 2s2. That's the last. That's the valence shell. This is the valence shell, and here we have 1, 2 for the 2s2, and 2p4 is this 1, 2, 3, and 4. So remember, always fill empty orbitals. Then with the leftovers, use to pair. Okay, so like I shown you here. So first fill always. So that's orbital diagrams of this. So what we see here is that this is unpaired and this is unpaired. They are wanting to pair. They are these two. So 2 unpaired electrons wanting to pair. And when we say when they are wanting to pair, that means that's where the bonds are formed. That's where the bonding occurs, the bonds form. So where are they going to get those 2 unpaired electrons, those 2 electrons? They are going to get it from magnesium. So here you have magnesium. Let's do this again. Magnesium giving away 2 electrons. So magnesium then, magnesium is 12, magnesium becomes 10, and it acquires +2 charges, right? And it begins to look like, you know, the neon, and we already saw that neon 10, it begins to look like neon 10. Okay, and that is, it begins to look like neon 10, and that is a noble gas, which we already looked up here. We discussed that. And then it has another piece for magnesium +2 is this is magnesium +2. These are the 2 electrons it got rid of. So then it has like the 8 electrons. So magnesium +2. So we got that one. Now, where do these electrons go? These are acquired by oxygen. Oxygen has 6 electrons in the last shell. So it accepts those 2 electrons from magnesium. This is oxygen 8. Then oxygen becomes 10 with -2 charge, and it has now 8 electrons. Oxygen 1, 2, 3, 4, 5, 6, 7, 8, and this is -2 and 10. And then internally, then it looks like neon. So it has that nearest noble gas configuration. It has the octet. This is the 8 electrons in oxygen. It has the octet met. Magnesium also has the octet met. This is the 8 electrons for magnesium. So that's the octet. When it loses electron, it gets the octet. Oxygen is wanting to fill these 2 electrons, and these 2 electrons are coming from here. These 2 electrons that magnesium gives are used to make the bond formation with oxygen. So here we will see that oxygen now has the electronic configuration of 1s2, 2s2, 2p6. Remember, oxygen is with 2 negative charges. So it is going to be like this. And it looks like it has got 10 electrons. So 10 electrons are 6 plus 2 plus 2 is 10 electrons. 10 electrons in the oxygen. And we have now oxygen looking like 1, 1, 2, 3. So this is 1s2, this is 2s2, and this is 2p6. And they are all of them. 2s2 is this, and p6 is this, paired. So those 2 electrons that were given by magnesium come here. You see? So these 2 electrons, they come here. Okay? And that gives oxygen its 2 negative charges. So these 2 electrons are this and this from the up top part, which we covered, these guys. Okay. All right. So we will cover this more right now. I'm going to just hold on to it. We are going to look at the formulas and naming in, my next video, because this is very extensive anyways. So we will cover this in the actual nomenclature, but we are going to continue with this. So I'm going to write down here to be continued. So right now you understand what I have explained first of all, then will come the formula. Okay, guys? All right. Thank you for watching. Take care. Bye-bye.